Hello guys, today we are gonna go through the work and energy in the second part of it, which is power and the remaining parts. The first title is power. Power is the term provides a useful basis for choosing the type of motor or machine which is required to do a certain amount of work in a given time. So as we remember our physics 1 class, power is the work with the divided by time is like work divided by time. It was given us the power, right? So this here in dynamics is a little bit specific, which is the derivative form we need to consider. The power generated by a machine or engine that performs an amount of work du, which is the infinitesimal work, within the time interval, which is the dt, which is the time integral, the change of time. So the power is equal to du over dt in derivative form, or if we know in the macro scale is du, which is the change of work over change of time. A given time period, it's just changing work. So when you add this one to the upside, du is equal to F multiplied by dr, which is we know that the work is F multiplied by dr from our previous example. So the power is F dr over dt, which is dr dt. dr dt, we know that the position with change of time is given as velocity, which is power is equal to F dot product velocity, which is our second formula. This is the first formula, and this is the second formula. If we have a motion with external force, is gonna give us the power. Hence, power is a scalar because F dot V is gonna give us scalar quantity, where in this formulation V represent the velocity of the particle which is acted upon by the force. We know that F dot V is the dot product, so it's gonna be when I, which x direction multiplied by x direction, is gonna give us unit vector of 1, and then we are gonna add j, d, and k. If we multiply I with the j, which is x direction multiplied by y direction, is gonna give us 0. So it's the basically projection of force with velocity multiplication, and is given the some units, which is 1 watt is equal to 1 joule over second, or 1 Newton meter per second, and 1 horsepower is 746 watts. If we go through the efficiency, where if there is power, we need to know that this power's efficiency, if there is an engine or motor, we need to know how much power we put and how much we get. This is the giving us the efficiency, right? And in the definition, the mechanical efficiency of a machine is defined as the ratio of the output of usable power produced by the machine to the input of power supplied to the machine. So it's gonna be power output over power input is gonna give us efficiency. Let's give an example. Let's say we obtain 70 horsepower from a car, but is an electrical motor, electrical engine inside this vehicle, and its input is 100 horsepower, but it reflects the output of 70 horsepower, which is due to like the friction and then the heat loss and blah blah. So we can say is 0.7 or 70% efficient of this system. If energy supply to the machine occurs during the same time interval at which it is drawn, then the efficiency may also be expressed in terms of the ratio of energy output of energy input. So we know that power is delta U over delta T, right? And here, and delta U, let's say 1, and this one is 2 delta T. So when you cancel delta T, if there is like same time interval, then delta U1 over delta U2, U1 over U2 is gonna give us efficiency again, which is depicted in this sentence. So instead of using the power output and power input, if you have energy output and an energy input, so you will have the efficiency of this machine as well. Power output will be less than power input, and so the efficiency of a machine is always less than 1. Only Carnot engine is gonna give us 1, but it's imaginary system, so we just neglect it, because in real life it's always whatever you put inside is gonna give us less energy or less power than whatever we put it, because there is gonna be loss due to the friction, due to the heat loss, due to the machinery loss, and blah blah. So mechanical loss. So that's why we always getting less than 1 of this efficiency. Okay, let's solve one example. In this example, a 50 kilogram block A is hoisted by the pulley system and the motor M. The motor has an efficiency of 0.8, which is 80%. At this instant, point P on the cable has a velocity of 12 meters per second, which is increasing at a rate of 6 meters per second square, which is the acceleration. We need to neglect the mass of the pulleys and the cables. What do we need to find? The power supplied by to the motor at this instant. From the pulley system, our kinematics part, we know that we have this system. If we have this system, we are gonna take the if we have the motor, we are gonna take a constant point like P. So this motion is gonna be counted, right? So let's say this P, let's say we have an age, we start from here, the P is start from here and then down. So like, let's say the age is decreasing or whatever it is, okay? So we are gonna say SP, the distance is plus this, if we take the datum over here, and from the A over here too, let's say. So this one is also decreasing, right? So 1 and 2 SA is gonna be the total length of this pulley system. So it's gonna be from here, it's gonna come over here. This guy is gonna be moving systematically, sequentially, and there is a P, SP is gonna be, let's say it start here to here. So like the motion is gonna be, when we add SP, is gonna be total of the length of L. So if we take the first derivative, it's gonna be VP plus VA, sorry, it's gonna be 2SA, it's gonna be 2VA, is gonna be equal to 0. And if we take another derivation, A, acceleration of point B plus 2A, which is the motion of this block, is gonna be 0. If we take this AA on the left side, so we know that AP at point P is equal to minus, sorry, not AP, we know that AA we can calculate it, is going to be minus AP over 2, which is AP, we know that is 6 meter per second square. 6 minus 6 over 2 is going to be minus 3 meter per second square, is our block A's motion is minus, so it's going to be upward direction. Okay, so let's use our motion. So it's gonna be the total F acting on it in the y direction, all that stuff is gonna be equal to, let's say it's in the y direction, it's gonna be ma, right? So whatever the motion, if there is no motion, if there is no total motion, it's gonna be 0. If the total motion, total force is gonna be 0, that means it's in the equilibrium, right? But there is a motion in upside, and we know that from this cable there is, when we draw our free body diagram, the block A have 2T, which is 2 cable TT, and mg, which is the weight of the motion. So this force acting on it is result to goes up the upward direction by the ma, the mass multiplied by acceleration. So let's plug all these variables. So I will say 2t minus mg result to ma, right? So 2t, the block has 50 kilogram, 50 multiplied by 9.81, which is the gravitational acceleration, is equal to, again, 50 multiplied by 3, which is the block's acceleration, which we found here. Then why we are not putting minus? Because we put the upward direction positive, that's why we take 2t as positive. If we take negative here, we need to say mg minus 2t. Alright, from here we are gonna find t as 220.3 320.3 Newton. Okay, what we find here the tension on the cable T, and here also the tension of the cable, which is 320.3 Newton. So we are gonna find the power supply to the motor, and we will see the tension. We know the velocity also at the P, so we know that power output, this motor gives the output, is the force acting on it multiplied by the velocity, right? So basically force, which is the tension, is 320.3 multiplied by the velocity, which is 12 meter per second, and we can find over here the motor gives output power of 3.89, which is 3.9 kilowatt, 3.9, almost 3.9 kilowatt. We know that P input is P output over the efficiency, which is 3.9 over 0.8, and it's gonna be 4.8 kilowatt. So that shows that the motor has to run or give, or the capacity work in the capacity of 4.8, but it reflects the outside on the cable 3.9 kilowatts, so which brings this block A upward with 3 meter per second square. The second example is a car which is 2000 kilogram of sports car is given, and this increases its speed uniformly from rest to 25 meter per second in 30 seconds. The engine efficiency is 0.8. What we need to find the maximum power and the average power supplied by the engine. We are gonna find it. Let's draw our free body diagram. Let's say we have a car, which is the engine is gonna give force in this direction, right? Which is the force car. And due to the mg, so let's say we have a mass, the force is acting from this direction. Let's say from here is gonna be mg sine theta, right? If we take this one as a theta, we are gonna find it. We are gonna find theta is from arctangent. What is it? 1/10. So we can find the theta for over here. And mg sine theta is gonna be over here, right? And mg cosine theta is gonna be on the normal direction. But we don't have friction, so we don't need to find the cosine theta, but we need to find the mg sine theta because it gives force in the negative direction of the engine. Alright, let's using these terms, which is from rest to 25 meter per second in 30 seconds, in order to find the acceleration of this car. How we can find from our kinematics knowledge, v final is equal to the initial velocity plus at, which is acceleration multiplied by time. Initial velocity from rest, so it's gonna be 0. So velocity is 25, which is the final velocity, is equal to the acceleration of the car multiplied by 30 seconds, which is gonna give us the acceleration is 0.833 meter per second square. When we find our acceleration kinematics term, we are gonna right now do the kinetics part, which is the total force is gonna be equal to the mass of this object multiplied by the acceleration, which is given here. So if we put all these terms, which is Fc minus mg sine theta, mg sine theta is gonna be equal to ma, right? So Fc basically is equal to m is, let's put in the same parentheses 2000 parentheses of a, which is 0.833 0.833 plus 9.81 multiplied by sine theta, which is around like 5. Theta is around like 5 degrees, and the force acting on the car by the engine is 3619 when you apply this one, 3619 Newton. Okay. From our power findings, we know that the force of car multiplied by the velocity of the car, which is the maximum velocity, let's say, for the power, maximum power. So force of the car, we know that the maximum velocity is 25 meter per second, so it's gonna be P max. Let's say P max is gonna be 3619 multiplied by 25, which is P maximum is gonna be 90.47 kilowatt. 90.47 kilowatt. But with the efficiency, we need to plug. So the maximum power, the input, which is the given, right, by this guy, is gonna be 90.57 over the efficiency, which is 0.8. So the car engine needs to give 113 kilowatt in order to move this car from 0 to 25 meter per second in 30 seconds, or to provide for this one, to provide the 25 meter per second by these forces. When we see the average power is gonna be again the force acting on this car by the engine multiplied by the V average, which is 3619 multiplied by the V average is from 0 to 25, which is 20.5, right? Because it's uniformly increasing, so the average is gonna be in the middle. So it's gonna be 45.28 kilowatt, and like inside input as an average power is gonna be again like 56.5 kilowatt. When you divide it 0.8, it's gonna be having this power. All right. The next topic is conservative forces and potential energy. Conservative forces, and if the work of a force is independent of the path and depends only on the force's initial and final position on the path, then we can classify this force as a conservative forces. An example of conservative force: the weight of a particle and the force developed by a spring. The work done by the weight depends only on the vertical displacement of the weight, and the work done by a spring force depends only on the spring's elongation or compression. So it's only depends on the final and the initial and final path, right? Because of the potential differences. We don't care if it is spiral motion or like the path is like wavy or some stuff. And another one, in contrast to a conservative force, the force of friction exerted on a sliding object by a fixed surface. The work done by the frictional force depends on the path. The longer the path, the greater the work. Consequently, frictional forces are non-conservative. So when you go back to the initial position, your frictional force or frictional energy losses is not coming back. So you already losses that, and when you go back, you need to double your frictional force losses, energy losses, and the work is dissipated from the body in the form of heat. So like for example, you have an initial position, you slide down to an end of points. Let's say you have here, your object is here, and then you slide down till here, and due to the friction, the bottom of this object is getting heated. So the frictional forces is a frictional energy, or like whatever you call friction. Due to the frictional forces, the energy is loses by heat. When you bring back, is not the energy is not gaining again, but you will again loses due to the again. So it's gonna be hotter on this bottom surface. But in the potential energy, like for example, you have an object over here. So if you drop the height of this object from here to here, your potential energy here, let's say mgh1, and you drop it h2, if you bring back, you will gain again your potential energy. So it's not depends how your path is changing. So you will bring your uh, object like in this wavy rod or curvy rod, but your potential energy, if you bring it straight down, is going to be the same. But frictional forces, if you bring like this curvy rod, your frictional force is depends on the path, so you will lose more energy. Let's keep talking about like gravitational potential energy. If a particle is located at distance y above an arbitrarily selected datum, particle's weight w has positive gravitational potential energy. We substitute g, since this positive gravitational energy is shown Vg, since W has the capacity of doing positive work when the particle is moved back down to the datum. Likewise, if the particle is located at distance y below the datum, Vg is negative since the weight does negative work when the particle is moved back up to the datum. At the datum Vg is again is 0 when it's datum here. We draw here is like, let's take your datum here and then your particle over here. First, let's say your potential energy here due to the height is 0, so or it's in the level this on the surface, like that's why we say its potential energy due to this datum is 0. When you put a positive y direction, when you put up, so you bring potential energy on this particle, so it's gonna be a positive, your weight, the particle's weight multiplied by the distance on the vertical side. If it goes down, it's gonna be negative potential energy, because you made this particle losing its potential energy due to this data. How we are gonna calculate is just multiplying W, which is mg, and multiply by the height, which is the plus y, or you can just show h, so which is mgh. If you talk about elastic potential energy, is the basically same for the our weight gravitational potential energy, but the only difference is the datum we need to take the unstretched position of this spring. So if there is an unstretched position, so our elastic potential is 0. When we elongate, like when we stretch it to a certain distance, like plus s, is gonna give us, which we derived before, how we calculate the spring energy is 1 over 2 ks square, and if it is we compress it, so it's gonna be again 1 over 2 ks square, but it's gonna be again plus due to the here is written here E, which is elastic potential energy, is always positive, since in the deformed position the force of the spring has the capacity or potential for always doing positive work on the particle when the spring is returned to its unstretched position. What it means like when we stretch or when we compress, it's gonna try to come to our unstretched position, so it's gonna be like sinusoidal motion, right? Like wave motion, like it's gonna go and come back, go and come back, go and come back, till due to the friction is gonna like stay in the unstretched position. So it doesn't matter if you are stretch or compress, it's gonna gain an energy, not losing the energy. So our potential function is the total potential function is the gravitational potential plus the elastic potential. In the when we write in the description is in the general case, if a particle is subjected to both gravitational and elastic forces, the particle's potential energy can be expressed as a potential function, which is the algebraic sum of the gravitational potential energy and elastic potential energy. The work done by a conservative force in moving the particle from one point to another point is measured by the difference of this function, which is the change of the path, like from 1 to 2, the energy is equal to the first potential energy minus the second potential energy. When a particle is acted upon by a system of both conservative and non-conservative forces, the portion of the work done by the conservative forces can be written in terms of the difference in their potential energies, which is we showed just before, right? The change of the energy is equal to the first potential energy minus the second potential energy. The first position and the second position. So we know that this formula from our previous lectures, the first kinetic energy plus the first potential energy plus the internal energy, or like the energy change from 1 to 2 is going to be equal to the second kinetic energy plus second potential energy. Here, the total of U12 non-conservative terms is represent the work of the non-conservative forces acting on the particle. If only conservative forces do work, then we have the kinetic energy plus the potential energy is equal to kinetic energy, the second kinetic energy plus the second potential energy. So it's gonna go 0. This equation is referred to as the conservative of mechanical energy, or simply the conservative of energy. It states that during the motion, the sum of the particles' kinetic and potential energy remains constant. If we have system of particles, which is like we have a system which is consists of many particles, this subjected only to conservative forces, which is T1, the total of the kinetic energy of the first position plus the energy change is equal to the second kinetic energy, total kinetic energy, which is we can say the internal energy doesn't change, only it change of their potential energies. So it's gonna be total this system's particles total kinetic energy plus potential energy is equal to second position's kinetic energy and potential energy total of it. Here the sum of the system's initial kinetic and potential energies is equal to the sum of the system's final kinetic and potential energies. In other words, the total kinetic and total potential energy is constant. So when you subtract it, it's gonna be a constant number. Okay. As an example, the 4 kilogram color of C has a velocity of 2 meters per second at point A. The spring constant is 400 Newton per meter. The unstretched length of the spring is 0.2 meters. So this guy is 0.2 meters. We need to find the velocity of the color at point B. From conservation of energy, we know that at point A, kinetic energy plus the potential energy of this system is equal to at point B's kinetic energy plus at point B's potential energy. Okay, let's put this guy as a datum and then let's solve our question. So at this point, the kinetic energy, so which is TA, is equal to 1 over 2 m, which is the mass is 4 kilogram. So m, the velocity square, which is 2 meter per second square, right? Which is gonna be 4, is gonna be 8 Newton meter. Newton meter. So the potential energy of this point, we know that from here we have from if we take the datum of this point, so here is gonna be minus height, right? We are gonna add the potential energy, so which is 0.1 meter is gonna be m gh, which is m is again 4, g is 9.81, and we added h, which is 0.1 meter, which is in the positive direction, right? That is like if we take there is a positive potential energy it has, plus we have due to the spring, we have another potential, right? We have another potential, but it's not pulling. It's gonna be on the straight line. Is just gonna act on this side, like here, like it's gonna be here. So we just gonna neglect right now the spring potential over here, because it's gonna stretch here and then it want to from here 0.3, because 0.4 is that guy, and we have the length of 0.5 over here, so we will have the potential energy of the spring on the point B. So let's go to TB is gonna be 1 over 2 4 and VB, which we want to know square, right? And the potential energy of this guy is gonna be equal to 4 multiplied by 9.81 how is gonna be is gonna be 0.3 if we take from here, is gonna be minus 0.3, right? 0.3 is gonna be our potential energy plus 1 over 2 the spring constant, which is 400 Newton meter, multiplied by 0.5 minus the unstretched length 0.2, which is square. So okay, all right, but we need to put here, this is for the gravitational potential one, we need to put elastic one too, which is 1 over 2, again 400 for the elastic spring potential, and it's gonna be 0.2 minus 0.1 is gonna be 0 minus 0.1 because it's compressed, but we need to square it. All right, so we will use this equation and we will add it up. The first acceleration is 8, right? And from here is gonna be plus 2, and we add potential over here too. So let's calculate this one too, or just let me delete here. Okay, is equal to let me take this potential to here, like minus 0.3, so it's gonna be 0.4. I need to multiply over here, so it's gonna be on the right hand side. If I add these guys, it's gonna be 2.3 Newton meter. So it's gonna be here 2.3 Newton meter and 2.3 Newton meter plus it's gonna be 2 VA square, VB square. So VB is at point is gonna be 1.96 meter per second. 1.96 meter per second. Okay, let me go through again. What do we need to find? We at point A we see the kinetic energy, potential energy, which is from gravitational, and elastic, which is from the spring. As you see here, we added mgh. When we decrease here, we decrease it mgh to 0.3. So the differences, just we can say from, if you take the datum here, 0.4 if you want. And then we just put this right hand side for the B. Let's say we decrease the potential energy, but like how it's gonna be reflected, but we increase the elastic potential energy, then as you see, from the velocity from 2 meters per second, it decreased to 1.96 because all this energy goes to the spring potential. In the second example, we are gonna have a roller coaster which has 800 kilogram. The question is asking if we start our motion from point A with without initial velocity, with rest, which means like there is no initial velocity, then it release down, and then it wants this roller coaster travels to be without leaving the track and then come back. At C, it's asking the velocity. What is the velocity? So and it wants what is the minimum height in order to complete this track from B for this motion. As we know that we can solve this question from energy conservation TA, VA, right? At B point right now, B, TV, VB. If first of all we will start from A to B. So from A, the point A, there is no kinetic energy because it comes from the rest, but we have a potential which is mgh, which is 800 multiplied by 9.81, which is the gravitational acceleration, multiplied by the h, which is the height of point A. At TB, at this point also, what do we want? We want one velocity of B, right? So in order to like complete this track, so it's gonna be 1 over 2, again 800, which is m, and at velocity b square, and plus vb, which is again 800 m, 9.81, sorry, and we know the height of this guy is from here to here is like from VB is h from 20, right? This is h, so it decreases from here, so we can say either like let's say 20, same thing. And as we see here, we have two unknowns. We have this h and we have this vb square, so that means we need another equation. Therefore therefore we need to go to our from point C level, what we can find over there. Before we go through this one, we know that the free body diagram, let's draw this roller coaster for the motion. We know that there is an mg on the downside at point B, right? It's gonna be, wants to go down, and we want the normal force acting on it is gonna be around 0, because we don't want to act the centripetal force acting on this tray. So mg, which is 800 multiplied by 9.81, is gonna be equal to, because what we need to do, like we need to make it like a centripetal force is acting on the outside of this one, right? So it's gonna be 800 multiplied by VB square over the radius of curvature, which is 7.5. And therefore we have this equation, and then we can find VB as 8.57 meter per second. Okay, so from the kinetic part, we have this motion, the velocity in tangential velocity. We know that the mg is going down, but the centripetal force is acting outward, so we want this line is gonna be around 0 in order to like in equilibrium, and then there is no force acting downward or upward because of the minimum height. Therefore we find VB, and then when we plug VB over here, we are gonna find our H is gonna be 23.75 meters. 75 meters. So therefore, if we have the 23.75 meters, this guys is gonna come and then it will turn this point B without any dropping from this tray. And the other question was point C. So we know that right now everything from TA plus VA is equal to TC plus VC. TA from the rest is gonna be 0. We know right now the VA is 800 9.81 mgh, right? 9.81, and the H is 23.75. Let's plug here. 23.75 is equal to 1/2 mv square, which is 800 multiplied by vc square plus so it's gonna be 0, right? Like we don't have any more at this point. There is on the datum line, so there is no potential anymore, so it's gonna be 0. Therefore our VC, at point C, the velocity is gonna be 21.6 meters per second. 21.6 meter per second. We found all the questions asked.